Today I'd like to talk to you about photons. Remarkable little things. Packages of light, essentially, as they're known. Okay, so what are photons? Well, for a start, they're massless. They don't have any mass at all. Makes them pretty remarkable, really. But that's because they are debatable particles. They're essentially carriers of force. They are gauge bosons, in other words. They carry force, just like the gluon carries force, which we talked about last time when we were discussing quarks. Photons, gauge bosons, carriers of the electromagnetic field. Remember, there are four forces in nature. You've got the electromagnetic field, you've got gravity, the strong force and the weak force. So of those four forces, there may be other forces that we don't know about yet, but that's another story. We've got photons as carriers of the EM force. So this is representing very loosely a wave, and that really is the manner in which photons are most comfortable. They exist as waves. They exist as particles predominantly when they're in experimental situations, such as double slit, when you're firing a particle at two slits in the screen and it decides to become a wave so that it can travel through them both at the same time. You look up double slit if you've never seen one before, fascinating experiment. Essentially that means that the waveform is the most comfortable medium for the photon to exist in, because it's a gauge boson. It's not really a particle very comfortably, unless it's being confined around a particle accelerator at certain, in which case, different kind of fish. Okay, so this is the waveform that photon is most comfortable in. This represents the EM field, okay, the electromagnetic field spectrum. This spectrum goes from radio, very slow waves, to faster waves, faster still, increasing in frequency and intensity until eventually they become gamma rays, which is the other end of the spectrum. So this whole spectrum is comprised of photons. We see a little slice of it that's just about, probably about there, which is visible light. So that's what we encounter, visible light, photons in the format that we are familiar with. Okay, there's a lot of debate with regards to photons, because obviously as the carriers of light, as light itself, it travels at the speed of light. And scientists are debating how much force they can exert as they do what they do. And the theory goes that it's the velocity of the speed at which they travel that gives them this energy. However, there are other possibilities, and I'd like to introduce some of them today. This line here represents something called the zero-point field. If you haven't heard of the zero-point field, Lynn McTaggart wrote a book on it called The Field, which is a very good read. I thoroughly recommend it. That's where I learned about zero point. And Tesla knew about it. He created experiments and potentially machinery that could tap into this infinite energy source, but he didn't get very far. So that's the zero-point field. So the zero-point field is something to consider in the matter of photons, how they travel, how they perform, what they do. Another thing that's worth bringing into the physics, metaphysics, quantum mechanics mix is what looks like slices of vague toast here, and these represent slices of what is known as the multiverse. Now, the multiverse is the potentially infinite array of universes in which the bulk exists, the bulk being the whole multiverse. But being potentially infinite, bulk might be a bit of a misnomer, really, because, you know, it's bigger than that. So anyway, these brains are the sections of the multiverse through which things may propagate. And there is a potential possibility that the movement or the transference between the brains of the multiverse could have something to do with energy and momentum as we see it in our own reality. Okay, so far we've got photons existing as waves, wave particle duality. You can go and look up wave particle duality for some nice surprises. It's the carrier of the electromagnetic field. Visible light is what we see, and the zero-point field and the multiverse are possible factors in the mix that we haven't considered yet. This is a representation of an explosion, and that is two particles coming together, smashing together, and annihilation is a feature of physics that happens potentially anywhere at all, because particles do annihilate with each other all the time, right across the universe. There isn't a limit to where or when this might happen. Potentially could happen anywhere, even inside us. Okay, when we are feeling up and we've got a lot of energy within ourselves, we are known as being bright and sunny. When our energy levels are low and we're feeling depressed and down, we're gloomy, potentially dark, in a dark place. Why is that? Does that have anything to do with our energy photon quotient? Well, these annihilations are very often metaphored in something called a Feynman's diagram. Now, this is a representation, a sketched representation of a Feynman's diagram. The Wikipedia version of it is what I've reproduced here, and Wikipedia gives a really good description of what a Feynman's diagram is. It was invented by Richard Feynman in about 1938, and it's been a mainstay of physics ever since. So anywhere you investigate physics, if you go into the academia and the scientific papers, you're going to come across a lot of these things, so it's well worth knowing how they work. It's spelt like this. So that's what you want to look up if you want to know more about Feynman's diagrams. Now, in this example, which is particularly pertinent to what we're talking about today, photons, you have an annihilation between the electron, which you're familiar with. This is a negatively charged particle. Its opposite number, its antiparticle, represented here by E+, positive, is the positron. So the positron and the electron are particle and antiparticle of each other. So they come into contact, they annihilate. The positron, bear in mind, can come into this universe from any potential source elsewhere. Think about this multiverse possibility, the zero-point field, yeah, could come from any number of places, this positron. But it appears in this universe, and immediately that it does, it meets an electron, and they annihilate. When they do so, they produce a photon. Is this little wavy line representing the photon, and that very quickly decays, using the scientific term, into a quark, an antiquark. So there you have this annihilation process producing a quark and an antiquark, which again are particle and antiparticle of each other. And this antiquark also produces a gluon. And gluons are also gauge bosons. They are also massless particles. Another interesting thing about this particular annihilation process that's very well worth bringing into the equation is that the electron, which we're familiar with, our own universe, you remember, travels forwards in time. But the positron, this stranger coming in from other places and being annihilated by the electron, travels backwards in time. So they annihilate, they meet. You've now got the present, which is this photon, and immediately after this present moment, when the photon is produced, you've then got a quark, which also is travelling forwards in time, and the antiquark, which is travelling backwards in time. So what happens to this gluon? Where does that go? Does this gluon end up stuck into our universe, or does it go into a different one? What happens to it from this annihilation? There are the questions. In a nutshell, there are some of the facts. This is what we know about the photon. I'm sure there's lots more to know about the photon than we actually have covered. How do we see colour? Because colour is essentially an illusion. Well, we see colour because the photons that are streaming across all the material that we see is reflecting off the atomic structure of that material in a certain way at a certain angle in order to reflect a certain portion of the colour spectrum. So colour itself doesn't exist. It's a complete illusion fabricated by the rods and cones and the retina of our eyes. Photons, remarkable things. Don't take them for granted. There is a lot more to the photon than meets the eye. If you'd like to discuss this stuff, please join the Quantumology group on Facebook. You can also find Quantumology on your search engine. You just punch in Quantumology, you can come across the website. And I'll see you next time. Thank you very much. Bye.